Thanks for coming to this very interesting session on mines and ammonia. We've got people a couple more minutes to come in. Let's go for it? Okay, we're going to go for it. Okay. I'm your moderator, I'm Dave Robbins. Hi, thanks for coming. Just a couple of housekeeping points. I was asked by Dr. Strande to mention that tomorrow we're starting at 9 o'clock. I think it's kind of said 8:30 or something, but that's not correct. Nobody will be here at 9 o'clock tomorrow. And then the other thing that she reminded me of was that we want to remember that we're trying to do our 3 key points for the takeaways from this session. So please take notes, because it falls on me afterwards. I have to come up with the 3 and give it to her. So I'll ask you if you can help me with those 3 key points for the takeaways. So this is a topic on mine and ammonia pathogen reduction. It's very interesting to me. I think both of these technologies have the potential for really being useful at scale for fecal sludge treatment in developing countries, especially in the low resource settings. But people really need to understand what those limitations are and how to use the materials properly. And I think we're going to learn a lot about how to do that exactly right here. So our first speaker, we'll get right to it. This is, our first speaker is, yes, Annika Norden. And I just saw her poster presentation. It's a very interesting topic. And she's going to be talking today about the inactivation of Ascaris eggs and salmonella by ammonia sanitation of black water. That's correct, right?
Yeah.
Okay. So
thank you for that introduction. Yeah, I'm here to present this work on behalf of the authors, the other authors, and specifically Jörgen Finland that has been doing this, performing this study. So a bit short introduction to the topic. We are all aware of that we are contaminating our environment by having fecal sludge disposed into water sources and into the environment in general. This causes both disease transmission and also eutrophication. And on the other hand, we have a large part of the population that is underfed and do not have enough food to eat. So, since we all excrete feces and urine, we have fertilizer locally available. And if we sanitize this, we can have a safe reuse of these nutrients. The reuse could also be an incentive to actually treat this waste. So ammonia is quite well known to sanitize, to inactivate pathogens from different groups, including viruses, bacteria, protozoa, and helminth eggs. And the source of ammonia can be, as in source of urine, originating from the urine, or it can be added as urea, which is the most common nitrogen fertilizer globally, or it can be added as ammonia solution. However, since the ammonia is volatile, it's problematic to add it as a solution, so it's quite convenient to use urea to treat fecal waste. And it degrades into ammonia first when it's in contact with fecal enzymes. So that gives a way to mix it in without being exposed to ammonia gas. So some techniques and principles, that is the ammonia in the uncharged form that is pathogenic, that is toxic to the pathogens, whereas the ammonium ion can be taken out as a plant nutrient. So we want to have as much of the ammonia in the form that is toxic, and that equilibrium is the pH and temperature dependent. That is, in a way, a simplification, but the higher the pH and the higher the temperature, the more ammonia is in the toxic form that actually inactivates the pathogens. But since that sort of ammonia is also volatile, you have to have the treatment closed to not lose the ammonia. And the effect of the pathogens, that will also mean that if you lose ammonia, the nitrogen content decreases on your fertilizer product. And the aim of this study was to investigate how low could the urea dose be to inactivate, to treat black water. And in this presentation, black water is used, and it represents a mix of urine and mixed with flush water, at 15 liters per day in person. And this is a laboratory study where urea and urease was added, and also Ascaris eggs and salmonella, since they were not present in the material at the beginning. And this slurry was stored at 20 liters FSM3, and the concentration of salmonella and the Ascaris viability was monitored over 50 days. So this is the sum of the results. You can see on the nearest graph the Ascaris egg, the viability, how it decreases, and how fast it decreases depends on the dose of urea. Whereas for the salmonella, you can see that some kind of a threshold concentration was found, like with 0.4 percentage of urea, the inactivation is quite fast and doesn't differ that much from the higher additions because it's rather sensitive to ammonia. Whereas with a low dose of 0.15 percentage, the inactivation was not that much faster than compared to the control that did not have any urea added to the toilet waste. And if you want to estimate for how long time you should treat this toilet waste to achieve the US EPA Class A criteria for sludge, which is less than 3 most probable number of salmonella per 4 gram of dry matter. It was estimated that a 6-log reduction of salmonella could represent that end concentration. And regarding helminth egg, to reach 1 helminth egg per 4 grams of dry matter, it was estimated that a 4-log reduction of the egg viability was needed. And with a urea dose of 0.4%, that would take 45 days at 28 degrees. Whereas if the temperatures increased to 33 degrees, it would only take 20 days. And another way to speed up would be to add more urea. So if 0.75% of urea is added, then the treatment time at 28 could be decreased from 45 days to 29 days. And some practical considerations. In this study, the pathogens was added to the material after the urea was hydrolyzed. In such a material where you have a quite diluted toilet waste, the presence of these urease enzymes are low, so it may take a time before the urea has degraded. And also, it was observed if the urea dose was quite low, then the pH dropped quite fast, and then the resulting ammonia NH3 concentration became too low to be efficient to inactivate the pathogen. And also stressed again that it's very important to perform this treatment in a closed way. So some implementation potential. If you have source separating plumbing, then you could separate your toilet waste from the rest of the wastewater from the household. So you could still have the convenience of having a flush toilet. In Sweden, apparently, it's has been difficult to have a shift into dry toilets when people already have flush toilets. And especially when you build new houses, even though if you don't implement this immediately, you could do separating plumbing. And instead of having a septic tank, it could be closed holding tanks with 2 chambers, so you could alternately fill one and then treat it while you fill out the other and reuse the nutrients. So, the major conclusion is that it's possible, at this temperature, it's possible to sanitize with quite low doses of urea, 0.4%. And that, of course, minimizes the cost. And probably the pH stability will be the limiter on how low you can go in urea addition. But it's also worth mentioning that it's quite a diluted material. If you have a fecal sludge with a high dry matter content, probably you need more to achieve the pH you want. Thank you. And I also put in the contact to the mail order. There is further in detail questions, and also the homepage to our group studying reuse and sanitation.
Just for a minute and see if you have any questions. Dr. Strande.
Hi, I'm Linda Strand with Sonic AFI. I was just wondering if the 0.4% urea addition is the amount that would come from one person's urine to also neutralize their feces, or if it would be addition of extra urea.
It was additional urea, and there is studies that show that if you use very low amount of flush water, you could actually use the urea and then the nitrogen from the urine to sanitize the amount of feces that you excrete. That is enough, but you have to keep the flush volumes very low, so that's critical.
Yeah, that's good to hear, because one thing that I always think is that to make nitrogen fixation in urea is one of the most energy-intensive processes in the whole world. So then I wonder, is it sustainable if you have to add urea? But obviously, if it could be the urea from someone's own urine, then it's not an issue.
And it's really sustainable and less dependent on external sources. But if you reuse this nitrogen, you can see that you just like use it earlier. You start using it in the toilet instead of starting at the field. But there are also studies where in urine diverting toilets, where the fecal fraction is not, it doesn't compose enough, it doesn't get high temperature during the composting to inactivate the aspartate. Part of the urine is used to sanitize it. And since the volumes are reduced, you don't have to use all the urine, so that's also a way to go. There are many options.
It's pretty neat technology. Any other questions? Yes.
I'll follow up on the same question. So, what is the initial urea content in your waste, original waste? It's not 0.4%, but it's 0.1, 0.4. How much do you need to add to reach 0.4%? A related question is, do you also have any mixing or shear in your system to break up the large particles? And that's very important in achieving inactivation.
In this study, it was a laboratory study in a small scale. But if you scale up, you have to encounter for that like sedimentation and uneven distribution. But actually, this 0.4% of nitrogen of urea, it was only coming from the addition. So there were already some nitrogen from the urine and from the feces in the material to start with. I don't know it by heart, but I can provide you this information later.
Any other questions for Annika? Yes.
You did a study of 50 days. Did you notice that there might be any adaptation of bacteria getting used to these concentrations and then in fact become resistant against your disinfectant?
It has been observed for enterococci that they tend to adapt, and also if you study enterococci that's naturally present in septic systems and urine tanks, they seem to be more tolerate ammonia better. But this is also a relevant question when you go from the lab scale to the field scale. Because in this study we added the pathogens, so it's also very important to verify when they're present naturally.
Because this will have a big impact in the pituitary, which you never empty completely, and you will have a source of pathogen bacteria, and they will survive. And in fact, you will get a completely resistant system against your urea.
I think there are so many full-scale studies that we could see that quite many are inactivated and do not adapt. But enterococci, we see that there's increased resistance.
We have time for one more question. Anybody for Annika? We'll have another chance during the panel discussion. Yes, sir. One more question.
I know that for poopy systems, you have some in the back some urea for you to the poop. If you are in the arsenal systems, you don't have these bags ready. What do you advise if someone has a bag and one dies? How scarcity of urine and that?
Yeah, but it may be different to those, the urea. But if you estimate how much of urine that is excreted over 1 day in relation to the excretant.
Can you say this quantity of
Not all the urine excreted during 1 day is needed to sanitize the feces. But I cannot give you exactly now by heart, but I could provide you with a reference.
Thank you very much, Annika. Could we give her a round of applause, please? One more little piece of housekeeping. If you'll see on your agenda, Dr. Vietnam was supposed to speak at the end of this session, but I think it was a double booking, or he's already spoken on that topic. So if you're waiting with bated breath to hear Dr. Nam, I'm sorry that we won't be having that discussion. Oh, he's in session 2, but I shouldn't tell you that because I don't see, well, now we are seeing a bad exodus. Anyway, I'll introduce the next speaker, who is Dr. Irina Chakraborty from IDE in Phnom Penh, Cambodia, and she will be speaking on the treatment of sludge, household trials using lime. So please, thank you.
Hello everyone, thanks very much. So yeah, I'll be describing some results that we have from a study looking at households using lime to treat sludge and some agricultural trials. And I'm going to this
Slide.
Okay. So, some background. Over the last few years, latrine usage has grown tremendously in Cambodia, but the sludge management options are quite limited. Pump trucks are expensive or not available in a lot of areas, and both individual users and professionals will empty pits with no protection, as we saw in some of the earlier talks. In both cases, sludge is often disposed of unsafely. So what we want to do here is treat the sludge so that no matter how you choose to dispose of it later on, you have some level of protection to the person handling the sludge, as well as the effects on the environment after disposal. So this is a typical latrine in Cambodia. It's a pour-flush squat pan. This is what the inside looks like. So you have the squat pan that has a chamber box, a concrete box underneath, and it feeds into typically a 3-ring pit made out of concrete. And you can see it's sealed from the top, but it actually infiltrates from the bottom. So the reason to use hydrated lime, CaOH2, for wastewater treatment and sludge treatment is basically inactivates pathogens and reduces odors. These are the 2 key characteristics. It's quite widely available, at a quite low price. In Cambodia, a lot of users are familiar with the fact that it does have disinfecting properties. It's quite often used for disinfecting animal shelters and for disinfecting fish ponds as well. There's also some reuse of fecal waste in agriculture that is accepted. It's very geographically varied. In some areas it's quite widely accepted. In other areas people are very reluctant to reuse waste. Another reason why lime-treated waste is appealing is because a lot of the agricultural soils are acidic and limit crop yields around Cambodia. So actually applying lime, even without sludge, just limes itself is a recommended practice to increase soil pH. So we have here lime-treated waste with potential as a soil amendment that both adds nutrients and raises the pH to improve yields, and also reduces the risk of using untreated sludge and disposing of untreated sludge. So the objectives here are to evaluate the feasibility of applying lime to pits on a household level, so have individuals do this. Look at resource recovery and usage, and a section of this project is looking at marketing lime to households. The first section of this project was some bench scale results, some lab tests on fecal waste with lime. This was presented at the WEGA conference in September, and that's available for those of you who are interested. Today I'll mainly talk about the agricultural trials, where we looked at using treated waste amended soil and its effect on corn, yields of corn, and also looking at the results of these household trials. Okay. So for the agricultural section, we want to demonstrate the use of lime-treated sludge in agriculture and quantify the effects on crop growth and yield. So we basically mixed lime with some sludge that we purchased. This basically caused a lot of the solids to settle, so then we applied just a clear supernatant to the soil. The reason why we chose corn as the plant was because it's quite commonly used as animal fodder. So this would actually further reduce the barrier to actually using it on the crop. And it would, so it's not being directly consumed by humans, but it in effect does return the nutrients to the soil and increases the nutritional status of the household doing this. Also, corn is quite sensitive to nitrogen concentration, so this was somewhere a crop that would demonstrate whether or not this is a feasible approach. So we had some plots here with randomly assigned lime and sludge and controls. Those results we're collecting now because the corn is still growing, but we do see some differences already. So basically we're looking at things like the width of the leaves, the coloration of the leaves, the height of the plants, and so on. And then later on in the growth cycle, we'll be looking at the number of tassels, how long it took for tassels to start to appear, and the actual yield of the corn. It does look like the treatment is doing quite a bit better. So for the household tests, here's some information on that. So we wanted to compare a few different lime application protocols to be used by households, and also interview households on their attitudes toward lime and waste reuse. basically based on the bench scale results, we had a value of about 1.5% weight per volume of the lime to use. So volume waste, weight of the mass of lime per volume of waste. This was enough to raise the pH to 12, which eliminates most pathogens given a sufficient contact time. For bacterial viruses, this is on the order of hours, and for something like Ascaris eggs, it's on the order of a week or two. This has also been shown by a few other groups. Another important parameter is having enough liquid. So this doesn't work well with a very solid sludge. You need enough water in order to make sure that the lime is distributed well throughout the sludge. And also, the higher concentration of solids that you have in your sludge, the more lime you need to neutralize those solids. So this is for the household study. We basically had 4 different groups. Old latrine users, so latrines that are more than 2 years old. These latrines, so we had 56 households where we added 1 25 kilo bag of lime to a very approximate concentration of about 4% weight per volume. These concentrations are higher than what we just saw because there's variation in the lime sold on the market. So this was to account for that and also to account for differences in sludge characteristics and the size of the pits and so on. So half the households, 56 of those households, had 1 bag of lime, 1 25 kilo bag of lime added. The other half had 2 bags of lime added. 39 new latrines, so these latrines that were built and in use less than 4 or fewer months ago. They, in those households, we had the users, the actual household users, add the lime as a slurry through the pan. Some were asked to add it at every use, and the other half were asked to add it on a weekly basis. So sort of like when you clean your toilet once a week, you would add a prescribed amount of lime. And this was at approximately 5% weight to volume percentage. So this was what the household was given. Basically, a 20-liter bucket. It contained a 30% slurry of lime and a scoop. And we asked them to basically put a certain number of scoops after they do a number 2. So these were the study areas. It's in 2 different districts, about 40 kilometers apart, with Phnom Penh in the middle. These are quite rural areas. So initially we conducted interviews with the households, then provided instructions for them on how to use the lime or applied the lime for them, and then returned weekly to measure the pH in the pit to see how well this was working. It also measured the amount of lime left in these buckets to see how well the users were actually following our instructions. And then we conducted a second interview with the households to get an idea of what their experience was like using the lime. So just some brief results. For adding the lime directly to the pits, so these are the households that had the trees that have been in use for at least 2 years. So with the blue bars are 1 bag and the orange bars are 2 bags. Adding 2 bags basically raised 100% of the latrines in one of the districts. So I'm just focusing on the subset of the results here. 100% of the latrines of the pits achieved a pH of 12. So we consider that to be sort of a high level of disinfection. With 1 bag, it was about 60%. Then we wanted to see how long that increase in pH persists. So by week 2, 3, and 4, you can see the numbers falling slightly. With just the 1 bag of lime added, by week 3, there are no longer any pits with pH of 12 or more. Now these are some of the results for adding the lime through the pan. Here we're expecting to see an increase in pH. As households keep doing this, the pH in the pit increases. So the weekly additions seem to be working a lot better than the per use addition. This might also have something to do with our weekly visits, so that probably acts as a reminder for the household to then add the lime. For the per use edition, households probably, or users probably forget to do it on a regular basis. So with the weekly usage, we had up to 25% now of the pits reaching the pH of 12. Some of the other things that became apparent during the study. So the tops of the pits are sealed completely during installation, including the very small cover on the top of the pit, which should in theory be left unsealed to allow for emptying, but you have the picture here again, you can see during the installation everything is sealed with mortar. This is mainly because of safety concerns. Families are very scared of kids getting into the pit, falling into the pit. There's also, we talked about, John presented about the flooding conditions in Cambodia, so families are also concerned about overflow during the flooding season, so they want everything to be sealed. They might stop to use the latrine during floods, but obviously they don't want anything to be coming out of the pit. On the other hand, most households are very willing to break the pits. We asked them if we couldn't, they were sure. They were keen to do that. We promised to fix them, of course. There was actually some level of the secret waste, although in general a much lower level of solid waste, because as you can see, since there's a pour flush with a trap, people don't have the kind of instinct to put anything large down that, but you know, there are some feminine hygiene products and things like that that do make it to the pits. And this is relevant to how lime may not be very easy to add directly to the pits, because as we heard earlier, there's a very high diversity in the kinds of sludges that are present in a lot of these pits, so it varied greatly between completely solid, something that you could only be able to shovel, something that couldn't be mixed, to kind of a very liquid layer and a solid bottom, to completely liquid all the way down, even though, like I said, these toilets have been used for at least 2 years or longer. So some conclusions on the technical scale: mixing is a big challenge for adding lime directly to the pits. And on a user basis, the weekly edition seems the most promising. There is also potential for technological intervention to improve compliance. So one of the ideas we're considering now is maybe designing some sort of flushing mechanism. So the lime is added when you flush the toilet. It's not something you have to think about as a separate action. And it would also be an easier way to flush than pouring with some sort of scoop as is done currently. The user feedback, all the users had very positive impressions of using lime. They said that it made their toilets smell less and that it killed germs. They were quite comfortable handling the lime slurry, but they were quite wary of the lime dust. Our research assistants made the slurry for them and were instructed on how to do that safely, but it does emphasize the importance of the slurry, because the lime produces a very fine powder that's very irritating and very difficult to keep out of your face, really. There is a risk of inaccurate dosing due to the settling of the lime. Lime isn't very soluble, and we asked the users to mix and resuspend the lime before applying it, but this wasn't always done correctly. The cost of materials when using lime where the user was applying it was about $2 per month, so it could potentially be a feasible approach. The other potential application here is for non-infiltrating or completely sealed systems, as it would provide an effective treatment of the liquid phase and reduce the need for emptying on a very regular basis. Reuse of the liquid phase seemed especially promising because it was very easy to apply. there was a very high nitrogen content. We measured ammonia most frequently, and it was between 200 and 1,000 milligrams per liter. In part because the lime actually helps to release a lot of the ammonia. The indicator level in this liquid phase was very low. And also because it is a completely clear liquid, it looks just like water, there's nothing floating in it. There's much less of this disgust factor that a lot of the users mentioned when we asked them about reuse. So in that sense, using a very clear liquid has more potential than asking somebody to deal with a more sludgy looking product. At the moment, we have ongoing supply chain research and doing some more detailed characterization of the actual lime-treated sludge, and continuing with the agricultural trials, looking at the effect on yield and the growth rate. And also, ID's HCD lab in Compass is doing some market research and product design, looking at how best lime could be applied. And then further work beyond the scope of this includes looking at the eventual disposal of the sludge, of the lime-treated sludge, as well as better characterizing properties of the sludge in existing pits. That's all. Thank you.
Do you have time for a couple questions? Let's go for Dr. Chapter 14.
I'm Dr. Colin from Wageningen University. I have two questions. You just mentioned that a sealed pit needs less emptying. That I don't understand.
Right, so in a situation where you wanted to have a completely sealed pit that wasn't infiltrating, being able to remove some of the liquid safely would mean that you would need to empty it very frequently. Yeah.
When you raise the pH to 12, all biological functions, not only the pathogens, cease being.
Everything does.
Isn't that a problem that the sludge is in fact not stabilized? And then you apply it to the land where it becomes a very nice breeding ground on the field.
A breeding ground for
any bacteria.
Well, yes, because it's nutrient rich. So it's
just then less contained.
well, I mean, it would be an issue if there was something being infected, like if there was another source of pathogens.
There are a lot of pathogens in soil.
Yeah, I mean, yeah, we can discuss this.
I could mention that EPA has done some work on this, and after lime stabilized sludge is finished with the stabilization, the regrowth is very low for most. Question?
Bond Energy, chair of the IEA sludge management group. So lime treatment makes a lot of sense for people sludge management. But one of the disadvantages of lime in the context that you're using it, it is extremely corrosive. And so you have something that is pH 12, 13, and this is a long-term storage system. And there's research that shows that it basically eats concrete something around quarter of an inch every year. And also there's the plastic pipes, etc. And another concern is if you give lime in the slurry form to people, their kids, it is corrosive on the skin, and so there is some potential risks there as well. But what could potentially make more sense or make the system maybe more sustainable in terms of operation in the long term is to collect the fecal sludge and then have it lime treated by in a decentralized facility. And so there you can also introduce mixing, proper mixing, proper lime dosage. So it is a neat system, but in terms of operation, I think there are some challenges that we will run into after a couple of years.
Yeah, thank you.
Any other questions for Dr. Chakrabarti? Yes.
My name is Ahmed Goma. I'm from FSM3. I wanted to know, you showed the variations that you encountered in pathogens. So some are, they infiltrate a lot and they're basically solid. And you also said it doesn't really work in those circumstances. So how did you deal with that? What did that mean for your trial?
Well, initially we were trying to select pits that did have enough liquid for us to try to mix the lime in. But yeah, I mean, I think this just showed that this is something that can be applied easily to all pits. So again, maybe if it is a very specific reason why certain pits infiltrate or exfiltrate a lot quicker, then those pits selectively might be more suitable for a treatment like this.
Thank you very much. We'll have more chance to ask questions at the end. Okay, thank you. One more piece of housekeeping news is that the UNESCO IHE meeting will be at 6 o'clock in the lobby today. I've asked you if I was supposed to announce that, and you said yes. Okay, forget that. That was for me. For people who are going to be in course. Exactly. Okay, let's introduce the next speaker, who is Grover Hector Mamani Casilla, and he will be speaking about lactic acid fermentation, urea, and lime. Promising fecal sludge sanitization methods for emerging situations. Thank you, sir.
Good afternoon, ladies and gentlemen. I will do the presentation on behalf of the team which conducted this research. The names are mentioned. My name is Grover. I'm working in the Waste, Netherlands. And I'm very happy that the two presentations conducted by these ladies was very good information to present this research. Well, what we are going to present here is the results of 3 different research. A little bit about the background. These treatment methods were investigated based on looking for some options to treat fecal sludge in emergencies. That's why we have 4 criteria, which is very important for us at the time to decide which methods could be used. The first one is it should be safe. The sanitization was a key factor. Also, the treatment should be robust enough because there are different types of emergencies and different types of fecal sludge. And the deployment should be easy to transport. Well, at Waste, we developed 3 different research. One was applying these 3 methods at pit latrines. I'm not going to present it. The second was the pit emptying, which was presented by my colleague yesterday. And right now I'm going to present the treatment methods. A little bit about the characteristics of the fecal sludge. We tested these 3 methods first at lab scale in Netherlands, but also we tested in the field in Malawi, in Blantyre. We had 2 different types of fecal sludge. One is from household pits, and the other is from market pit latrines. Some differences you can see, for example, the sludge age. In a household pit latrines we have from 1 to 7 years. And in the public toilets, we can say first sludge 1 to 4 weeks. The main differences, of course, are the volatile solids. As you can see, there's a high concentration of volatile solids in the market latrines, and also the E. coli concentration. We used E. coli to check the pathogens. Well, let me talk about the three methods that we tested. The first one, the lactic acid fermentation. This method works because of the lactic acid process due to lactic acid bacteria. To apply this method, what we found first, we need an inoculum, a pre-culture. We prepared the inoculum with 30 ml of Yakult and 15 liters of milk. This pre-culture should be mixed and stored during 28 hours. Once we have it, we had 4 different reactors in a triplicate and 1 control. We filled the drums with sludge, and we added the 2 additives to use this method. The composition or the concentration was 10% weight to weight. Also, we had to add 10% of molasses in this case because to do this treatment method, we need a source of sugar for the lactic acid bacteria. We had an initial mixing of 3 minutes, and the containers were sealed. The samples were collected at 2 days, 4, 7, and 9 days. The results of this treatment method, first of all, the lactic acid concentration. As I mentioned, it was applied 10% of inoculum and 10% of molasses at the beginning, but the concentration was increasing during the monitoring period. As you can see, at day 9, it was 4,700 or 4,700 milligrams per liter of lactic acid. How it works with the pH? The pH started decreasing. It's the opposite. The lowest pH we reached, it was at day 9, almost 4.2. And the E. coli, we also checked the E. coli. What we found, that at day 7, between day 4 and 7, was not detected more E. coli. It was under less than the detecting limit. Of course, at the day 9 also it was not detected more E. coli. Those are the results of using this treatment method. A little bit about the costs. There are 2 components for this treatment method. The pre-culture, using the cost of Malawi, is around 32 euros to treat 1 cubic meter of fecal sludge. And for molasses, it was 2 euros for 1 cubic meter of sludge. A little bit about urea treatment. The process was already explained in the presentation before, which was very good. What we found for urea, we also played with different concentrations, and we found that 2.5% in terms of weight is a good concentration, because we are looking a treatment method in emergencies. It should be fast, and we will see that we reach in more or less 4 days the completely sanitization of the fecal sludge. It was mixed the same like lactic acid bacteria, and we monitored the same period of time. The pH, as you can see, it was an increase of pH. In the first 2 days there is a significant increase, but after that the pH is more or less, it remains stable at 9, more than 9. The concentration of ammonia, as you can see also, it increased during the monitoring time. And what about E. coli? I told you before, between day 2 and day 4, we didn't detect more E. coli. The concentrations are mentioned here. That's why we can say to use this treatment method using 2.5% concentration of urea, it's possible to sanitize the fecal sludge in 4 days. About the cost, because we just need to add urea, the common urea which is used in agriculture, it was approximately 20 euros to treat 1 cubic meter of fecal sludge. The last treatment method, lime, what we tested, we played with different pH to check the capacity to sanitize fecal sludge. We filled the containers with sludge. We added different concentrations of lime. The range of concentrations was between 1.2 to 1.6 in terms of percentage of weight to weight that we added to reach different pH. And we mixed and also monitored. The results are the monitoring time was just 5 hours because this treatment method is quite fast. After 1 hour in our reactor, which is under pH 11 and 12, it was free of pathogens. There was not more pathogens detected here. The reactor, which was under pH 10, after 5 hours was free of pathogens. About the costs, based in local cost in Malawi, to treat 1 cubic meter of fecal sludge, it's approximately 12 euros. Well, summary of these treatment methods. These treatment methods are able to sanitize fecal sludge. Of course, lime is faster. In 1 hour we can have free of pathogens, but urea takes 4 days and lactic acid takes 7 days. The NPH also is very important to mention because we have to look for some other solutions for a final disposal because are very acid or very basic the final products. As you can see, with the treatment method based on lactic acid, we have a final pH of 4, and for urea pH is 9, and for lime pH is 11. The costs, it was mentioned, lactic acid at 34 euros per cubic meter of sludge. For urea is 20, and for lime 12. Based on our 4 parameters, we can say that the three treatment methods are safe. It can be done safely. We can reach the concentrations of E. coli as are required in the regulations. These treatment methods are robust because we deal with different kind of fecal sludge, and we got good results in all of them. And it's easy to deploy. For example, thinking on lactic acid was the idea. You just take your small bottle of Yakult and travel to the place, mix it with milk, and you prepare your inoculum, and you can start treating. And also the lime and urea most of the time are available locally. This is summary and acknowledgements for the team who work in this research. We have a master student from UNESCO IHE, also from TU Delft, Waste, and the local authorities of Blantyre City Council who collaborated in this. Thank you very much.
A couple of questions. I know there is many. This is very interesting. Dr. Nassim.
Hi, my name is Jenna. I'm from the University of Agricultural Sciences in Sweden. And I was wondering if there's a difference between using the lactic acid versus just another acid, and if that may be
cheaper.
Okay. Why lactic acid? Well, about the cost. Of course, there is a lot of potential to do more research. For example, there is an option to reuse the treated fecal sludge, which has the lactic acid bacteria, as inoculum for the next batch. There is that option. And also there are different sources of sugar. For example, organic waste has also source of sugar. That's why there is a lot of potential to do more research in order to optimize this treatment method.
Yes, Esther, hold on.
Hi, I'm Esther from Oxfam. We actually use slide stabilization plants in the Philippines as part of the emergency response to the typhoon. And the joy of light stabilization is how quickly it's treated. But as you showed, the pH level is extremely high, and that's a bit of a problem for disposing of it or reusing. All your other tests were done in the sealed drugs. It's really nice to see the breakdowns in day and cost of material. Because for me, that's all I really want to know. But what I would like to know is, in this, you're just looking at these sealed 200 litre drums, not even slightly smaller. What's the possibility for making it a larger scale treatment so that it can really be used for emergency situations from a practical point of view?
Okay, because this project is part of a big project called Speed Kits, an emergency sanitation project, we are also developing raised latrines and pumping machines, all the components of the sanitation chain. The idea was to collect, for example, in emergencies, sludge in this kind of containers. Then we can apply, let's say, at this scale, the treatment. Maybe it will be a lot of effort applying this. But also, this is one of the next steps, the way forward. We're looking to apply this treatment or to test it at larger scale. It could be with 10 cubic meters tanks, or of course each method has advantages and disadvantages. For example, some of them are very fast, or they take more time. With the urea treatment, we need a closed container, for example, but you have potential for reuse. There is a lot of opportunities to do, but I will take advantage of your question to ask if in the audience there is people who's working in this kind of projects in emergencies, or it could be also in the unplanned urban settings that where you can see it's a potential to apply these methods at large scale. We're looking for partners to do this. That's the next stage of the project. Thank you.
Okay, thank you very much. And we'll have another chance to ask questions. One more question. Okay.
Hi, Ray from the UKF Switzerland. So I just wanted to know if you thought about, because it seems to be a reproducible experimental setup. So have you thought about looking at more resistant pathogens like Ascaris? Yeah.
Yeah, it's a good question. We were looking at that, but during the research period in Malawi, there was no the equipment to do the helminth X, for example, to test it. However, it's also very important to consider that fecal sludge is very different. I think we are doing a lot of research, which is really good. I think after some time we will have at least ranges of the best concentration to apply one method, but it can change a lot because of the fecal sludge characteristics are not unique, and the conditions, the operation conditions also are very, very variable.
Okay, last question until the panel discussion. Here, you can use this one.
So this is more of a comment, and I kind of keep seeing this throughout the conference. Fecal sludge is a relatively new term, but we have been doing sludge treatment and management for a very, very long time. It's a very old field, and there's lots of research, very good research going back to the 60s. So there's lots of research done with lime and lactic acid for treatment of primary sludge, for treatment of septic sludge, and there's lots of data available on a whole range of pathogens. So this is very interesting research, and it is very important to have on-site applications, unique applications, but we should not reinvent the wheel. The knowledge is available out there. Maybe some of them are not in electronic databases, some of it is older research, but it is, I think, important to do a true literature review and see what is available and build on that rather than reinventing the wheel. Thank you.
Well, actually, we did a lot of literature review, but this is a summary of 3 research theses. I didn't do all the research, but I really appreciate your recommendation.
Let's just leave it there right now, and we can. That was a very good point. Thank you very much. Thank you. Good to see you. Because we have time and we wanted to give you your money's worth, the organizers asked if I could do a quick presentation on Oxfam's use of line stabilization. It only take about 10 minutes, but it does put me in an awkward position because I'm your moderator. So Jonathan has agreed to moderate from here on, and I'll just give a quick presentation on that.
Thank you very much. Well, I would just like to introduce David Robbins.
Okay, so
my job.
Oh, good. Go ahead.
No, it's not my job.
Okay.
Yes, I'll do the question, but it's got to make the presentation first.
Okay, so about a year and a couple months ago, the big typhoon Haiyan came through the Philippines, and Oxfam was actually one of the first on the ground after about a week. They came in and they set up a couple of line stabilization systems because all of these very good, well-meaning aid organizations kept bringing toilets in, but there was no place to treat the waste. So this is one of the senior operators of the line treatment system in Tacloban, and she's using a pH meter, which is really one of the critical pieces of technology for running this process. And they're relatively inexpensive. The pH meter costs about $130, but it lasts a lifetime. So this is just a real quick presentation of what we're doing with Lyme as we scale up through 14 municipalities that were devastated by the typhoon. Let's see, I should be able to do this myself, right? No. Okay. So, you know, we're not prescribing any of the municipalities that they have to use Lyme, but what we wanted to do is a cost-benefit analysis for several different technologies, so we can really look at what are the costs and how do they really rate. So here we looked at an aerobic treatment type of a system, a anaerobic system through lagoons, what we call a hybrid system, which is using a combination of the two, and a fully mechanized system. And what you can see is we've really looked at the costs, and these are in pesos, but we checked it for 5 cubic meters per day, 10 cubic meters, 15 cubic meters, and 30 cubic meters per day of septage. And we looked at the cost. 3 million pesos is about $75,000, Jay, something like that. Jay is from the Philippines, he's got the conversion down. But what was really nice was with the Lyme stabilization, the cost is affordable. Well, it's the least expensive at 2 million pesos for, say, the 5 cubic meter, but if you compare the amount of land required for the system, those two factors, the low cost and the small footprint, make the technology attractive, at least to the point that it's worth looking at a little bit further. So this is something about the different kinds of Lyme, and it's important to note that when we're talking about Lyme stabilization, at least for our purposes, we're using the hydrated Lyme, which is the calcium hydroxide. The process doesn't work that well if you're just using the agricultural agricultural lime, which is a little bit different. And the image is a one-step line stabilization process where the reaction occurs right in a trench. Now, in an emergency situation, if you can get 20 guys and gals together with shovels, you can dig a trench pretty quickly. Here, these guys had the access to heavy equipment, which made that easier. But it's basically dumping the fecal sludge into the trench, mixing the lime in, and then after a few days, covering that trench and digging another trench. This is very, very simple, low cost, easy, fast method of treating and disinfecting your wastewater. This is the pit that they actually built. Oxfam, the team, built this little pit for a two-step process, which is reacting the pit and then drying it in sand filters, which is what they've been doing in Tacloban ever since the disaster. Now, you can see this guy mixing the lime by hand, and I'll tell you what happens after they mix it. They have a pump. They'll let it settle for a day, and then they'll pump off the supernatant, and then manually cart out the solids to a drying bed where it bakes in the sun. That really is not the best system, but that's what they're doing until they can come up with something better. At least it's treating the waste, and it's being done pretty low cost right now. Let me just mention that the protocol for lime stabilization from EPA anyway, is that you raise the pH of the lime up to a pH of 12, as we've discussed, and keep it there for 30 minutes. And that does kill off most of the pathogens, not all of them, and it does prevent regrowth of the organisms to some extent. And it only takes about 10 to 20 kilograms of hydrated lime per 1,000 liters of 4,000 liters, 1,000 gallons basically, 4,000 liters of sludge. So as Oxfam plans to scale up, we're trying to do this in a more organized fashion that is compliant for meeting discharge standards in the Philippines. So these, these wastewater systems, these are wastewater systems that are going to be discharging into the surface waters of the Philippines, and there are standards. So 50 milligrams per liter BOD or less, depending on the water course. So we have pre-treatment screening for the sludge that comes in. We've got the reactor tanks, we've got sand drying beds, and then secondary treatment through like a constructed wetland cell or even a sewage lagoon, something like that. And these will be undertaken in the 14 communities where we're working. Now this is an image of a very cool looking sand filter from EPA, which doesn't use any kind of underdrain pipe, which is inexpensive to install. And you can see that it just slopes down to a little gravel sump there after the effluent passes through the sand is collected, and then it can discharge to the next treatment stage, which in this case will be a small constructed wetland cell. So low-cost technology, no pipes needed. And one of the things that the folks in the Philippines are facing is, where are we going to put this thing? So you saw the poster out front, which says the "Not in My Backyard" syndrome. If you haven't, that's a great poster that my colleague Jay came up with. The NIMBY syndrome. Nobody wants this thing in their backyards. But we've got to put it somewhere, and one of the things we've got to figure out is how big of a space do we really need. So we've come up with this simple chart based on the volume, and this image is a site plan from the proposed facility in Tacloban. You can see the existing buildings where the reactor pits are, the sand filters, and then they've got a little wetland cell before it discharges into the creek. And this can tell you about how big of a site you need, figuring that you need to still walk around these units, maybe even take a hand cart or even a pickup truck to move the sludge around after it's dry, etc., and for parking and whatnot. So there's just a little handy guidance right there on how big the site needs to be. And I think this is my last slide. This is showing you the incorrect way of adding lime to fecal sludge. I went in there and I can still taste the lime in my mouth after like a month. But really what they should be doing is mixing up a slurry and putting that into the fecal sludge and mixing it up that way. But they are using their safety equipment, or most of it anyway, and this is, I think, our project with Oxfam as we scale up. So anyway, thanks so much. There's that website right there if you want to learn more about that program. It's all up on the website.
Thank you very much, David. I should say, although I work for Oxfam, I now know as much about this as you do. Linda's got a question. Burning question.
Thank you, David. That was a great presentation. I had an information request a couple of months ago from the International Red Cross asking how they should treat their fecal sludge for Ebola clinics. And I was wondering if you thought this would be a good solution for such an application.
I do think so. I don't know that it's really going to deactivate the virus. I don't know anything about it. Maybe you guys have more information. But as far as fecal sludge goes, it's a great way of, putting up one of the things you can put these up really quickly, as Oxfam has shown, as opposed to the other technologies take a little bit more planning and construction. So for rapid deployment and ease of operation, I think it's pretty good. And I mean, if there was an extra concern about the pathogenic nature of Ebola, you could react it in the lime a little bit longer and probably achieve. I would imagine it would work quite well.
Thank you. Thanks. Very relevant question, and I must admit I was thinking along the same lines. The applicability to the Ebola is a major issue, continues to be a major issue, so it's obviously something we need to look at. Yes, please.
Sorry, maybe I missed it. What do you do with the effluent? You said you dump it off the top, and then where does it go?
Right. Well, in the emergency, where it was going was in the ditch and untreated untreated other than lime into the waters, the surface waters. So, because it was an emergency, the regulators sort of looked the other way. It's not the correct way to do this. So that's why when we scale up, we're going to have to do the full treatment. So under the correct system, the effluent would go to, the waste goes to the sand filter. The effluent passes through the sand, is collected either in the under drain or in the sump, and then goes to a secondary treatment like a wetland cell, and becomes treated to the point where it can be discharged in compliance. Is that what you want to know?
Yeah, and I'm just curious about the high pH and bring that into wetlands. How is that impacting?
That's a good point. The pH, it drops down, and it's a plant that they use in the Philippines called tambo. Tambo. It's like a reed. I think it's some kind of a reed. It's extremely resilient. Now we haven't really tried it with high pH yet, but I have a feeling it's going to work quite well. And if it doesn't work as a constructed wetlands, it'll work as a gravel filter. So I believe that we'll get the treatment that we need. We'll have to check it, we'll have to see. And if not, we'll need to have an additional type of a treatment method because we have to have a discharge permit. Something like a surface flow constructed wetlands or a shallow holding pond to allow the pH to drop down a little bit more, become more disinfected by the UV rays of the sun, sort of act like a sewage lagoon. That could be another secondary treatment method to achieve the discharge standard. So some of this is a work in progress. We don't have all the answers yet. Good point, though. Any other questions?
I'm just thinking, should we invite the other presenters? Have we got time for?
We have time to bring them up.
Perhaps it would be appropriate now to invite the other presenters up.
Can we all come up?
Okay, we've got how long have we got? timekeeper. So, well, we have our panel here, so would we like to continue the discussion? Do you have a microphone? Yes, do please, go ahead.
I have a more general question to all of you. I'm just wondering about the impacts of this treatment on greenhouse gas emissions. With the increase of pH, there's potentially more ammonia being released into the environment. Not so important for actual fecal waste management, but I was just curious if that's been assessed in any of these treatments.
Then I start to answer from what we know so far. There are some studies investigating greenhouse gases from sludge from sewage treatment plants when it's stored. And there it has been shown that when it's treated with ammonia, the greenhouse gases are less compared to ordinary just storage.
Just regarding with the ammonia treatment, yeah, we know this is a toxic material, and this is the main treatment, or the treatments conducted because of this gas. That's why one of our findings was we need a closed container to improve the treatment. And of course, we still need to work in the procedure, how to proceed it, because if we close a container, it will be under pressure. And in order to discharge and to follow the next steps to final disposal, it still need to do some research on this thing.
I can add in some observations, like when we do these ammonia treatments, we do not have that much of gas evolving from the fecal sludges, but when we want to have control, that is a problem, because sometimes these jars burst due to the gas that's used.
And when we applied the water over the sludge after treating the sludge with lime, we actually did it over a mulch, so that would reduce the volatilization from the soil surface.
Hello, I'm Sri Saxena from University of Delaware. I had a very general question in terms of using lime stabilization for container-based on-site solutions. I just wanted to know if it is a possible solution to remove odors in those sort of technologies.
Yeah, there definitely is a reduction in odor, but in the case of a mixed urine and fecal stream, you do get so much ammonia production that the ammonia odor more than offsets any benefits of any reduction in sulfidate compound.
We have one experience testing the lime in the public toilet, the market. We conducted also some research. Well, the method to determine the odor, it's very subjective because it's conducted, it depends on how people feel about it. But following the existing methods, we got good results. Of course, that is one of the main advantages of using lime. It reduces significantly the odor.
Maybe I'll just add a little bit on the odor discussion. So lime treatment kills pathogens, but after land application, it is notorious for odor generation because all the organic matter is there and eventually it decays. So maybe odor is, yes, ammonia is an issue. So an odor generation right after lime application, because it kills all bacteria, it is not an issue initially, but it will be an issue after land application. And that's one of the disadvantages of lime treatment, at least in North America, that farmers and they complain. So it's a great solution. And all metals, there's no silver bullet, there's pros and cons. It's a maybe quick and dirty method, but it certainly has its place, and its greatest advantage is it kills the pathogens.
That's a good point. I wonder if the farmers would plow the fields under, if that would eliminate that problem that you mentioned.
It does minimize it, but not still.
And regarding ammonia treated waste, it smells ammonia, not surprisingly. But also, when it's applied on the field, it should be incorporated fast to not lose the nitrogen, and that would also reduce the smell. So that's the recommendation that is applied.
There's been a few references to EPA. David, you mentioned EPA. I'm interested to know, is this something that's used extensively in the United States, or is it something that's now fallen by the wayside? These references seem to be quite old, so what's the current situation in the States with regard to the line application?
Well, I can tell you I did a little research when I found out I had to moderate this session, and back in 2009, the EPA estimated that 20% of all the biosolids generated in the world were treated with lime. So this is not new technology, it's used all over the place. You guys are going to go, some of you, to the Bai Chai treatment plant in Halong Bay. Anybody going to that one? Nobody's going? One person? Well, that's too bad. That's a really cool place. And there they've got a big lime stabilization system, a big lime silo that you can see, and so it's used quite frequently.
Does anybody else have something to comment on that? We're back to the
So it is used a lot in North America, and what determines the use is the size of the treatment plant. So it is very commonly used for small-scale rural treatment plants because it is the easiest thing to do. It doesn't require any infrastructure. There's almost no cost, and you just apply lime and you're done within a couple of hours. But not so much for larger treatment plants, but still in North America it is used a lot.
I just want to add one experience more. It was used in Haiti in the outbreak of cholera. It was a very fast solution, easy to apply, and a good solution for the moment.
This about lime. I want to comment in addition to the research suggestions. Lime will kill completely the important bacteria, so therefore it is very difficult to use to further treat with natural systems like construct water. Either the water has to be mixed with, after neutralizing with an acid, mixed with another wastewater, it is possible to treat it. Otherwise, bacteria are not there, so there is no way of doing it. But you can see lime is very important from this presentation. For cases like UDDT toilets, where feces is separated from urine, one of the major problems in feces is there is a lot of pathogen in it. Disinfection is very difficult, and it is also highly concentrated. If we use lime, it is very easy to co-compost it, maybe with let's say solid waste, so that it can be applied as a fertilizer. But for larger systems, as it was mentioned before, like if the water is too much, it is very horrible. How can we treat the organic matter? It is difficult to remove it. So maybe this can be.
Is there any particular response or comments in response to that?
From Sandex. I'm just wondering, most of the pathogenic bacteria are gram-negative, but the gram-positive bacteria is more tolerant against pH compared to gram-positive. Gram-positive bacteria is more tolerant, but in the evaluation of Lyme treatment, you are using only coliform, that is gram-negative bacteria. Why don't you, is it necessary to check the evaluation of gram-positive bacteria as well?
I cannot give you maybe the answer that you're waiting for. But why, in our case, to see the effectiveness of the treatment method in terms of pathogen reduction, why we use E. coli? Because it's very difficult to determine all the different types of microorganisms which are present. Why E. coli is used? Because there is a standard method. Even this method is very subjective. It depends how do you perform. It could vary. Doing the same method, the replication, you can get different values. Because up to now, there are new technologies to determine other types of bacteria, but for now, we use because there is mentioned in the standards, and we can say the results we can compare with the guidelines. That was the main reason for using E. coli, and not looking for different types of bacteria.
Yeah, I understand the E. coli is a standardized indicator, but I think in the case of high pH treatment, is it still okay not to use gram-positive indicator bacteria like enterococcus?
Yeah, I think we should consider also your point, but yeah, we didn't, at least in the research that I presented, we didn't consider that point.
I think I did come across a reference where they looked at a broader range of active pathogens, and basically the mechanism is independent of whether the organism was gram-positive or gram-negative. And yeah, you saw the contact time required is pretty low. I think there may have been a slight difference in the contact time required, so maybe an hour versus a half hour, but there wasn't a huge difference on a larger scale for the different kinds of pathogens and organisms.
So if I may add a little bit onto that, pH 12 will kill anything. What you need to play with is the time, contact time. And it's typically pH 12 for 2 hours, kills everything, including not only bacteria, but viruses, enteric viruses, protozoa, cysts, oocysts, and Hamiltova, and there's research that shows that.
I think it killed me as well. A question in relation to if we're using water to, if you've got a more compact sludge in the pit, and we're hearing that there's a need often to add water and then to agitate and mix. Is it therefore appropriate at that stage to kind of add a bit of lime during the process of getting this? On the one hand, we're hearing that it's good to add lime, but then we're mixing it anyway. So is there an opportunity there to add a slurry? Would that be a good thing to do?
You mean before they desludge?
During the process of desludging? Would that be?
Yeah, we look at that option. First of all, as it was mentioned before, mixing is a very important parameter to have an effective treatment method in using lime. And one of the ideas of, for example, as we developed the pumping machine as well, it was also mentioned that the lime is very corrosive, and there is a risk we can use at the same time of sludging or discharging the sludge into the treatment container or whatever. But there is a risk of affecting somehow the performance of the machine. Well, there is an option, but we have to consider some other factors.
Yeah, I like the fact that in your research you're kind of looking across the chain and not just the plant. Was there any other comments from on that point?
There's a practice where they will add the lime right to the truck and then put the fecal sludge in there. So mix the lime as the sludge is going to the truck. But in the U.S., that process has been banned in a number of states because of the corrosive nature of the lime that damages the equipment. And there may have been some health and safety reasons, but at least in a couple of states that they don't allow that anymore. So it's probably not the best way to do it, I would think. Thank you.
I guess any last question, otherwise we're sort of thinking about winding down for today. We've had a long day, but there's an opportunity for any last questions. Yes.
Maybe ash. Wood ash, can it be used as kind of substitute because it is
ash?
Ash. Wood ash.
Do we know that the content of ash is significantly high?
So ash would work in a similar way by raising the pH, but it doesn't get it anywhere near the 12, and 12 is kind of the killing zone that we're trying to achieve with lime. Also in the case of the source of ash, if you're in an area where there isn't a lot of wood burning or you don't want there to be a lot of wood burning, it could be a limiting supply. So it would be a different application protocol.
Okay, good. Well, I'm going to go and have a gin and lime soda. Thank you all very much. I will now hand back to David, who is the official chair of this meeting. So thank you very much for inviting me to stand in while you.
Thanks, Jonathan. And thanks to the audience. Appreciate all the really good questions and feedback. And thanks to the speakers. Enjoy your evening.